Hey guys, welcome back. We're going to discuss Chapter 4, Motion in Two Dimensions today. So previously we've been talking about motion in terms of horizontal plane or the vertical plane, but now we're going to look at what happens when they're moving in both planes, so at a diagonal. So let's get going, shall we? All right. So section 1, vectors in physics. First thing we should mention is that there are two major quantities in physics, and they are magnitude and direction. Now we can classify different dimensions, different types of measurements as scalar or as a vector. So scalar is when a quantity has magnitude, but no direction. So it's an amount, and that's it. So remember how we said speed was how fast you're going? And even volume is how much mass takes up a certain amount of space, as opposed to vector, which is looking at magnitude and direction. So, for example, velocity is a vector. Speed was just how fast you're going, but velocity was how fast are you going in a certain direction. Just like acceleration is a change in velocity, and velocity is a vector, so therefore acceleration is a vector. So resolving vectors. Nice thing about this is we can figure out what vectors are, and we can do that by dividing or breaking it down into its horizontal and its vertical components. So to resolve a vector means to find its components, the x component and the y component, the horizontal and the vertical. So what these are the lengths of the vector along specified directions. So again, horizontal direction, vertical direction. And as long as you know what R is the resultant. So if you look down here at the picture, R is the actual vector. So it is the what would become the hypotenuse of the triangle. Sorry, I got something in my eye. So as long as we know the actual vector itself and the angle that it's moving at, now that letter there looks like a 0 with a line through it. That's a Greek letter theta, and that stands for angle. That's the symbol we use for angle. So if I know that this resultant is 1.50 meters and it's at an angle of 25 degrees above the x-axis, I can figure out what the y and x components are. I'm going to talk about how we do that, but when we go through, do the math, we'll find out that the x is about 1.36 meters and the y is 0.634 meters. Now this is where having taken trigonometry could help, but even if you haven't, that's fine, because we're going to talk about the three functions, the three trigonometry functions that you need to know regardless. So if you've taken trigonometry before, you might know the term SOHCAHTOA, which is what's written across the top. And what that stands for is sine equals opposite over hypotenuse. So sine of theta, so sine of the angle, equals the opposite side over the hypotenuse. So to find the 0.634, we take the sine of the angle, and as long as we know the hypotenuse, we can rearrange the equation to solve for what that opposite side is. Again, I'm going to show you how that's done. So in other words, we can reduce this. Sine theta equals the y value, the y component of our resultant, divided by the resultant. Here we did so. Now cosine angle equals adjacent side over hypotenuse. So cosine of theta equals the adjacent side over the hypotenuse. Now this opposite and adjacent is referring to the angle. So remember, the angle is here. I'm looking at the picture. I have my mouse moving across it. The angle is there. Opposite that would be the y component. So our angle is here. Opposite is the y. Angle is here. Adjacent to it is our x value. So that's how we're getting how to know what adjacent versus opposite is. So cosine of theta equals the x component divided by the resultant. All right, let's take a little bit more look at this. So sine function, we use sine for the y component because more often than not, we're going to be looking at the angle that is opening up to the y side. So generally, good rule of thumb, use sine for the y component. So sine of the angle is equal to the opposite value, so the y component, divided by the hypotenuse. So what we have to do to rearrange that equation, in order to get opposite by itself, we'd multiply both sides by the hypotenuse, and we end up getting the opposite side, or y, equals the hypotenuse times the sine of the angle, theta. So sine theta times our hypotenuse will give us the y component. So taking the sine of this angle times the hypotenuse, it will actually calculate the length of that side. And then for the x component, it's the same thing, except you use cosine instead of sine. So you use the cosine for the x component. So the cosine of theta of our angle is equal to the adjacent, or x value, divided by our hypotenuse. So here's that equation. Cosine theta equals adjacent divided by hypotenuse. And you think of it as cosine theta equals x divided by hypotenuse. To get x by itself, multiply both sides by the hypotenuse, and you end up with x equals hypotenuse times the cosine of theta. All right, see, not too bad. So as long as you know what the hypotenuse, what your r value is, and you know the angle, you can find both the x and y component. Now, what if I don't have an angle? What if I don't give you tangent? Sorry, if I don't give you theta, but maybe I gave you the x and y components. Can you find the direction? Yeah, you can, because remember we said SOHCAHTOA. We talked about sine theta equals opposite over hypotenuse. Talked about cosine theta equals adjacent over hypotenuse. Now we have TOA, tangent theta equals opposite over adjacent. So all of this will only work for right triangles, by the way. And what we can do is we can use the inverse tangent, which is the opposite of tangent, in order to find the angle. Because remember, if we're talking about acceleration, or if we're talking about velocity, or if we're talking about displacement, those are vector quantities. They have magnitude and direction, so that means that you need to tell me what direction that quantity is going in. So if we use the last part of that SOHCAHTOA, TOA, or the tangent function, tangent theta equals the opposite divided by adjacent. So in other words, tangent theta equals the y component divided by the x component. Now, tangent isn't necessarily something you can divide by because it's a function. It's not a number, but you can take the inverse of it, and that's all in the calculator. I do have a video on how to do these functions on a particular calculator. So if you take the inverse of tangent to both sides, it'll cancel out on this side, and you're left with theta, your angle, equals the inverse tangent of the opposite divided by the adjacent. So inverse tangent times y divided by x. So to find this angle here, take the inverse tangent of this value divided by that value. Don't worry, we got videos to show you how to do that. All right, so what if we have a few different vectors and we're not quite sure how to get the resultants? So a great way to keep track of your vectors in any given situation or system is to create a diagram. And we'll draw the vectors as arrows. The point of the arrow is showing the direction that the vector is applied. So whether it's a force or a velocity, the arrow is showing you the direction of the vector. And you try and make the length of the arrow as proportional as possible to the vector's magnitude. So here in this situation, we're looking at this boat. The wind is pushing it this way, and the water is pushing it this way. So here's a good diagram. Yeah, now there's a few different ways you can draw it. You can draw it as the starting point. There's the vector for the current. There's the vector for the wind. Now just looking at those, I can tell two things. The direction, the wind is pushing this way, and the current is pushing this way. And since the current arrow is so much longer, I can tell that it's a lot stronger than the wind. And then we can figure out the resultant of it by essentially turning these into right triangles. And then drawing the arrow, the resultant, where they meet. Now another way you can do that is instead of putting this here, you can have it front to tail. So draw one, draw the other, make the triangle. You'll see me doing these in some of the videos. So don't stress too much. We're still gonna keep talking about them though. So for magnitude, it is ideal to scale down distances. Now, am I necessarily going to be all, with my ruler trying to see if it's an exact scale? No, I'm not. But it is good to try and keep it scaled down and proportional, just because it'll help you visualize it. For instance, if one force is being applied 20 newtons in one direction, and the other is 10 newtons in the opposite direction or in a different direction, we know that 10 is half of 20. So, good thing to try and keep those arrows proportional to each other. One is twice as big as the other. It's just good, like I said, for visualizing. So it kind of makes sense when you look at it and when you calculate it. For direction, use the angle to determine which way to draw it. If I give you the angle, you want to try drawing it as accurate as possible. Protractor is a great way to do that. So adding vectors. So if you want to be able to add vectors, then they have to be the same units and describe the same quantities, meaning that, let's say they're both for velocity. They are the same quantities. So great. But if one velocity is in meters per second and another velocity is in kilometers per hour, you're going to have a hard time adding them. So you would have to do some dimensional analysis to put them into the same units. Apart from that, like it says, same quantities, you can't add a velocity vector with a displacement vector. They have to be the same quantities, describe the same idea, as well as be composed of the same units. The resultant is the vector that represents the sum of two or more vectors. So here we have A and there's B. This green line is showing you the combination of A and B. So that's if they're going at angles. If they're going in straight lines, if they're going in the same direction, we have 1 plus 2 would give us, this would be our resultant vector. So we do also have what's called the triangle method of addition. For instance, we have 1, 2, 3, 4 vectors there. And this red one, that's the resultant. Now, how we could do this is, again, the triangle method. You're gonna draw the initial velocities or displacement, whatever the vectors are related to. You're gonna draw them head to tail, so like chains. And then what you can do is take and turn them into right triangles, which is why it's called the triangle method. And then use combine the different x and y values to find your resultant. We have a whole video on how to do that, so no worries, no stress. And that's what this one's talking about as well. What if the vectors are not perpendicular to each other? So if they're not perpendicular, they don't make a right triangle all on their own. So what you would have to do is that triangle method. So here we have this red one going up and then this red one going up. Now they are not perpendicular to them, so I can't use the regular, Pythagorean theorem and sine, cosine, theta yet. But what I could do is look at each vector individually, turn it into a right triangle, and find its own individual x and y values. So I find this x value and I find this y value. Then for this vector, I find its x value and its y value. Now their resultant is this green dotted line. So when I add the two x's together and add the two y's together, I now have a right triangle, a larger right triangle. And I can use that with this combined y and this combined x. I can use that with the Pythagorean theorem to figure out what the resultant would be. And I can also then figure out the angle theta. Here's another example. We have R1 is our first vector and R2 is our second vector. So what we would do, again, find the x and y's of each one. So here's the y of R1 and the x of R1. Here we have the x of R2 and the y of R1. Now, you notice the x values are going in opposite directions. And what do we say? How do we show an opposite direction? With the negative sign. So to the right would be positive plus this negative value. And then we have two y values going in the same direction, so we would add those together. If I was to drag this arrow over, it would fit nice and snug right there. And if I subtract this from this one down here, again, be about right there. So we would have this tall, thin right triangle. I can now find the resultant using Pythagorean theorem, and I can use inverse tangent with the y value and the x value to figure out what theta should be. Again, we have a video on how to do this. So this is just showing you different ways that you can kind of look at it and figure things out. So you can add them in any order. You can add F1, then F2, and then use that to figure out what your resultant would be. If you wanted to show them coming from the same point, then you just have to make the parallel lines to show where it would end up. I personally like this one better because it's easier. It's just connecting from one end to the next. I find it easier that way because then you just add the resultant from your starting point to your ending point. Order is independent of the sum. Kind of like if I was to add 2 plus 4 plus 2, I get 8. Well, what if I add 4 plus 2 plus 2? I still get 8. What if I add 2 plus 2 plus 4? I still get 8. So regardless of the order that you add them, you'll get the same magnitude, so long as you take into account directionality. So up and to the right would be positive, down or left would be negative. So again, this is just showing you we have these three vectors, and how can we go about using them? Well, we can look at here and here. It's just showing you the different ways to figure them out. That's all that this is showing you. We have a video, again, how to do this. Don't stress. Subtracting a vector, and this is what we were kind of already hinting at, is when you subtract a vector, it's not necessarily that you're truly subtracting it, but you are adding the opposite. So you are adding the negative. So again, same magnitude, we can have displacement in this direction and displacement in that direction. But since they're going in opposite directions, remember, how do we tell opposites? And in terms of directions, with a negative and positive sign. So to the right would be positive, which means that the value to the left would be negative. So you add them together still, but instead of adding two things that are going in the same direction, like 30 plus 30 would give us blah, blah. What it would be instead is 0 plus negative 30. Sorry, give me one. All right, sorry about that. My husband had called. So anyways, so when we talk about opposite directions, we'll think of it as one direction being positive and the opposite being negative. So if we're talking about 30 meters per second to the west, well, what's opposite of that? We can think of it as negative 30 meters per second west, or as positive 30 meters per second east. So how that would be like, if I'm traveling 30 meters per second in this direction, then I turn around and go 30 meters per second in the opposite direction, add the vectors, 30 plus negative 30. And that's just what we're talking about. Opposite directions, you add the, or you put it as a negative sign. Because positive and negatives show direction, not value. It's okay, Ripples. All right, relative motion. So observing velocity. Velocity measurements and observations differ in different frames of references. So what this means is if you are outside of the system and you are observing the system, the different quantities can appear different to you. So an object is dropped from a plane. From someone on the plane who's looking at the object as it's dropped, it'll look like the object is just going straight down. Because the person is moving with the plane, and actually so is the object, it still has that initial forward velocity, so it just kind of looks like it's going straight down. But to someone on the ground, it appears that it's going in this arcing motion, having both horizontal and vertical movements. So we can use these same basic techniques as in terms of finding vectors and combining them with one directional and two-dimensional velocities. It's just that the frame of reference is different. So it helps us to figure out, you know, how does the motion or the velocity appear to an outside observer? A lot of times you can use subscripts to help identify different velocities. So I can put this as V with a subscript C for car and V with a subscript P for police. So let's say we have car A is traveling at 80 kilometers per hour north and car B is traveling at 90 kilometers per hour south. How fast does car B appear to be traveling with respect to car A? So the velocity of B to A equals the velocity of car A plus the velocity of car B, because they're both going in the same plane. They're both, let's say, horizontal north or vertical north to south. Let's see, north, car A is traveling positive 80 because we said up would be considered positive. So plus 80 kilometers per hour plus negative 90 kilometers per hour because that one's heading south in the opposite direction. So the velocity of car B with respect to car A would be negative 10 kilometers per hour. All right, projectile motion. So in our previous chapter, we talked about one directional motion and including free fall, and we talked about the 1D equations. Well, those are difficult to use for two directional motion because instead of just looking at this or at this, we have to look at that. So we have to take into account two things. Therefore, it's easier to break the motion of an object down into components. And then once we break it down into components, we can now apply the equations for the X components as well as then for the Y components. Then we can recombine them just like before in order to find our resultants. So what is projectile motion? Projectile motion is a curved path an object follows when thrown, launched, or otherwise projected near the surface of the earth. It is subject to the laws of gravity. So in this case, the person throws it. They throw it up. Well, as soon as it leaves the person's hand, it still has that upward and angled velocity. However, at a certain point, gravity is going to overcome the velocity. It actually already starts overcoming it because as soon as it leaves the person's hand, it's going to start feeling the acceleration due to gravity. And as it gets higher, it's going to slow down, and then it's going to start speeding up vertically again, but it still has that horizontal component. So projectiles follow a curved path. We call this a parabola. If object has an initial horizontal velocity, then there will be a horizontal velocity throughout the entire path, which is why it keeps going farther away from the starting point. So here we see a cannonball is fired. It's fired and has an initial horizontal velocity of 20 meters per second. And at each time interval, guess what its horizontal velocity is? Its horizontal velocity is still 20 meters per second at every single time interval. Now we see the vertical velocity changing because gravity is affecting it and causing it to accelerate in the downward direction. So essentially, what we're talking about is projectile motion is free fall, but with horizontal velocity. So here we show an example. This is this red ball is demonstrating free fall. So it was just simply dropped. It had no horizontal velocity, and we notice that it's experiencing an acceleration in the downward direction thanks to gravity. Here we are showing that, well, what if a ball rose off a table? So it was already rolling horizontally and then it rolled off the table. Well, it still has this horizontal velocity, which is why instead of going straight down, it lands all the way over here. Does it have vertical velocity? No, because vertically it was at rest. It wasn't moving up and down until it rolled off the table. So because it doesn't have any initial vertical velocity, it will experience the exact same free fall acceleration, negative 9.8 meters per second squared. All of its motion before it reached the end of the table, all of its velocity was horizontally. There was no vertical component until it left the table. Once it left the table, the only thing acting on it vertically was gravity. So now we can kind of show you how they both look. So they both fall off the table at the same spot, but one was simply dropped and one was rolled off. Now if you notice, each time interval lines up. So we have 1 second, 2 seconds, 3, 4, 5, 6, 7, 8, 9, 10, 11. So they line up at each of the same time intervals at the same height above the ground. Because like I said, they are experiencing the same vertical acceleration, which is gravity pulling them down. The only difference between the two is this one ended up farther away from the table because of its initial horizontal velocity. But they'll still hit the ground at the same time. They'll just hit in different places. So these are some of the equations that we would use for projectile motions. Now for projectile motions, really the only thing we have to look at is, the velocity equation, Vx equals delta x over delta t. Kind of rearrange that to solve for the x position. And again, the reason for that being that the only thing we really have to worry about in terms of the x direction is it's a speed and where it lands. Whereas here we have to take into account the acceleration due to gravity. It's y velocity as a result. So it's vertical velocity as a result of the acceleration due to gravity and the time, just like how here, the time. Now that's more so if it's launched horizontally, so if it rolls off a table or is shot forward. But if it's shot upward at an angle, or if it's thrown upward at an angle like the baseball player, now we have to take into account that angle. Now these look scary. They do. But all that we've done is replaced Vx with the initial velocity cosine theta. So that's just us finding the x component of the initial velocity that's going at an angle. So that's all we're doing. We're replacing anywhere would say Vx with Vi, the initial velocity cosine theta. And that's just to find the x value. If we need to find the y component for the y equations, then wherever we would put Vy, it would be V initial sine theta. So if you notice, there really a lot of these are the exact same equations that we saw in the previous slide or in our previous chapter. We're just adding the sine theta and cosine theta. Not too scary, hopefully. We do have videos to help with this. First off, we have the Science in Pajama videos. These are the ones done by me. We have Intro to Two-Dimensional Motion. We have using trig functions on a calculator. I have a very basic scientific calculator, and I show you how to use the different functions on it. Resolving vectors and finding vectors practice. And we have adding and subtracting vectors. See, told you we have a video on this. Let's see, relative velocity practice. And we even have projectile motion practice. Then for the other videos, I'm just gonna kind of quickly read through them. Don't memorize scalar quantity and vector quantity, organic chemistry tutor, vectors, basic introduction, organic chemistry tutor, addition of vectors, Khan Academy, breaking down vectors into components, Cohen physics, resolving vectors, Illyria high physics, adding vectors that are not perpendicular, Matthew Cook, non-perpendicular vectors, organic chemistry tutor, projectile motion introduction, Khan Academy, horizontally launched projectile, Khan Academy projectile at an angle, and organic chemistry tutor, how to solve projectile motions. So we got lots of resources to help you out, to kind of provide extra examples and extra explanations. So hopefully those help. If not, hit me up in our Google Classroom, an email, or in our actual classroom. I will post the the link for this video in the video, for this Prezi in the video description. So you have access to all these links. And in the meantime, you guys just stay awesome, stay amazing, and most importantly, stay safe and healthy. Bye, guys. Take care of yourselves. Bye-bye.